Welcome to Earthfeed, From Soil to Shelf, where packaging expert and yoga enthusiast Kelly Williams helps small and medium brands transition to sustainable packaging. This podcast is brought to you by Earth First Compostable Packaging Solutions.
Welcome to the second episode of the Earthfeed podcast, From Soil to Shelf. This episode is going to be about where materials and infrastructure combine to rethink packaging and the way we manage packaging after we use it. And with me today is Dr. Evan White from the University of Georgia. He's an assistant research scientist and director of the Biosynetic Laboratory at UGA's New Materials Institute. Dr. White graduated from University of Georgia in 2014 with his PhD in chemistry after studying stimuli-responsive polymers. Current research efforts focus on designing and studying compostable packaging films. A member of the Institute's Technology Development and Implementation Division, his work focuses on translating innovative technologies from the laboratory to commercial viability and application. He works closely with the Institute's industry partners to study and advance biologically degradable chemistries used in single-use packaging. So obviously, an appropriate background for today's conversation. So thank you, Evan. Thanks for joining.
Yeah, thanks, Kelly, for having me on. And I don't think I can add too much more to that introduction.
Excellent. So let me start with, so I met you first, Evan, at the New Materials Institute, I think back in 2018, maybe?
Yeah, I think it was
Sound
2018.
About right? Yeah. And I had just gotten into the compostable side of packaging after having done flexible packaging application development for 27 years. For the last 6 or 7, it's been strictly in compostables. And as I'm starting to see patterns of challenges, I experienced the New Materials Institute and some of the great things that you're doing there, particularly the respirometers, which allow you to study conditions a lot at the same time. And we had kicked around the idea of, wouldn't it be great if we can take these mono and duplex and triplex laminated materials and study them in the same compost at the same time to really understand the way they break down? Because we had noticed that we had customers, converters, manufacturers of packaging that, one had submitted the same structure and it failed 2 times, another submits it to another lab and it passes. I'm like, well, how do we get a sense of what all of these conditions are? So we put together a proposal of how this would look. And I'll let you take it from there because it seemed to be pretty well timed to have that in hand. And then we'll walk it through to where we are today with it.
Yeah, and I think that's a good point to bring up the time of it. And also when you're studying systems biology, time is important. So what we wanted to do is leverage our support from both UGA, that was in part funding the effort from the Office of Research, and also our funding source from the Walmart Foundation to enable this work, and also the investment in respirometers that basically allows us to monitor the carbon from the sample plastic being converted into CO2 by microorganisms. That's ultimately what they do. And having a large respirometer bay built with our partner company in Slovenia, Echo Respirometers, Echo Instruments, they engaged with us to create really a large system, a 60-channel system that would allow us to study 60 individual reactors at a time. And when it comes to biology, it's good to have a lot of replications to validate your data. But that allowed us to do multiple samples at once against the exact same biology, the same compost at the same time. Because compost is a moving target, it's an evolving system. It's never static. The organisms are, the general classes of organisms stay the same, but they're always in flux and changing depending on the inputs. So really the best way to normalize all those complex variables is to just start with the same compost at the same time, and then do rounds of testing with a logical experimentation format where you only try to change one variable at a time per structure, and then you can screen 2 or 3 variables in different formats and garner some understandings about how these microorganisms do or do not break down this carbon source into CO2. And it was basically like rounds of testing for organic chemistry and weeding out the losers and figuring out what the higher performing formats are. And the higher performing meaning degrading more quickly in this compost environment. So the funding stimulation back in about 2018, 2019 from the Walmart Foundation and our partnership that was developing through some other programs like CB Squared, like National Science Foundation CB Squared program, that kind of enabled us to have the connection to say, hey, there's this need here with all of our industry partners, and this is everyone involved in the vertical supply chain, from raw material suppliers all the way up to converters. The stakeholders that make this packaging want to understand how does it degrade or does it not, and how can we engineer things for, say, industrial composting applications, which are great in play spaces and controlled spaces, and also with a goal of looking at home compostable options. It doesn't require the high temperature and structures that are a little bit more forgiving on I'll call it management in a home compost scenario, because there's basically little to no management at most home compost environments. So the temperatures of the compost testing that we were looking at was relevant to the industrial composting industry. So that's 58 Celsius. And 58 Celsius is the temperature that matches the North American and the European standard temperature for industrial compost testing. But basically, we wanted to introduce the more challenging temperatures, given that the biology was going to be well vetted, and we do a lot of screening to make sure that the biology has the right metabolic rate, elemental analysis is on point, carbon and nitrogen ratios look good, and we do a lot of testing on the chemistry and the biology of the inoculum to make sure that it's quality stuff. So we try to keep that as constant as we can throughout these rounds of tests, but ultimately it's the temperature was the variable that we tried to lower the furthest, and 20 Celsius is a challenging condition.
So before we get into what do we do with all of this information, I'm curious to hear some of your insights into what you learned from that. And I know at one point there was like, well, how do you know? I used to joke that it's like we're a bunch of US politicians and we don't know anything about our constituents, because those constituents are the ones that are voting on what they want. And I know there were some learnings there, but there's also genetic methods, right? So you can look at the genetics of the microorganisms before, after, during. And I was just curious if any of that was included. And then also if you could comment on there's ASTM methods that use the term biodegradation, but what they mean is getting into smaller pieces through environmental conditions that break it down into smaller pieces, mainly microplastics, where biodegradable means it actually is consumed as a food source for the microorganisms. But either way, if it is designed to be compostable or earth digestible, as you know, I like to use the term, at some point that actually has to go into a physical change as well, into smaller pieces and fragments. So if you could maybe glean some of the learnings that you found along the way, that would be, I think, really helpful to our audience.
Yeah, so I think since you bring up the terminology, I'll go to that first before I talk about the genetics. But ultimately, we try to follow the ASTM D6400 terminology in North America, and that defines compostable plastics as the what I think the American public's lexicon would understand as a biodegradable plastic. The understanding is that the plastic is returned to its smallest base unit. That monomer is carbon dioxide. It's basically the building block of life on Earth, and from the standpoint of carbon, and that's the ultimate oxidation product of respiration. So that's what consumers want, and that is the understanding of what a compostable plastic is. When it comes to biodegradable, there's a little bit less scrutiny. All compostable plastics are biodegradable in that they will fragment into those small pieces, just as a stump will turn into smaller pieces as well. They will fragment down into smaller pieces, natural products. That's a natural process of degradation, and biodegradation just means that it's a product that ultimately will break down into smaller and smaller pieces, and basically go and pass through a 5 millimeter sieve at the end of testing. And it's a good sign of the metabolism of that carbon source, but it's not proof of it. And a lot of products are biodegradable that are not compostable, and that is it's a nomenclature challenge to convey to consumers. But ultimately, what our target goal is and what consumers want is that compostable plastic. So biodegradable has been legislated out of marketing and some places in the country and in the world as well for this kind of greenwashing understanding of what biodegradable really means. Just because a polymer structure or a product breaks down into tiny microplastics or further nanoplastics doesn't mean that carbon source is wholly metabolized into CO2. You can pass the testing for biodegradation that way, but it doesn't necessarily mean you'll pass the respirometry testing, which is ultimately what that tool is used to understand, is where does the carbon go once it's broken down into very small pieces.
Am I accurate in saying that's probably the area that greenwashing most commonly sits, is using methods that show that it breaks down, but not that it composts?
Yeah, I mean, the old adage, out of sight, out of mind. It's if it fragments into particles you can't see, then for one thing, it's hard to measure, but it's not proof of metabolism, and that's really what consumers want, and the understandings that they want to have when they buy a product that makes that claim.
And that's where the respirometry comes in, right? Because you're measuring that it is producing. So if there's carbon there, microorganisms consume it, it goes to organic CO2. So it is very easy to understand, but I think there's a lot of confusion as to exactly how you do that. So I think you also learned during that test some interesting things like single materials and versus when you combine them together and the way they break down. So any insights that you can on that side be interesting.
Yeah, and I think we're still trying to have a better understanding of what the general rules are when you have mixed materials, but it's not a binary when it comes to including mixed materials for faster biodegradation. So some structures may biodegrade faster when they're mixed together with other chemistries, but that's not necessarily true. I think what we can say is that for some reason that we don't fully understand, the majority of the time when you put mixed materials together, so say cellulosics with polyesters, the overall structure will disintegrate and metabolize into CO2 faster than the original polyester on its own. And we've seen this happen in several cases, but it doesn't happen every time. So we don't fully understand why that is. But I think it's a good strategy to think about if you're trying to design compostable packaging. Why not mix materials for a better consortium of bacteria that digest those materials? And those are the organisms that are doing the work of degrading those polymers, and some are specialists and some are not. Some are generalists, and I think having a more diverse structure affords faster composting. Doesn't always happen, but that's some of the findings that we found from our work with the Walmart Foundation. So I think it was around 2020. Our sponsor, Walmart Foundation, came back to us and said, "Okay, great, you've helped design and study these compostable formats." And the elephant in the room is, where's the infrastructure to collect them? And where's the communication to consumers about how to dispose of them? And that is a significant problem. And it's part of solving this problem with the circular economy is you have to design on both ends. And when it comes to compostable plastics, the nice thing about their end-of-life future is that complex chemistries are allowed and actually desired, whereas in recycling you want monomaterials and massive. That's what recyclers want. They don't want contamination from other plastic streams. But when it comes to packaging, lightweight packaging, complexity is actually better. And that's what the organisms want. And also, if all those chemistries do truly compost and biodegrade into the base monomer CO2, then you have an opportunity there to have a really clean stream for a valued product over landfilling. So composting is kind of bottom of the list when it comes to diversion of food scraps. When it comes to feeding people or feeding animals or even generating energy, I think. But composting is always a better opportunity than landfilling, because landfilling is really the motivation of what we're trying to avoid with all of our food scraps. And that's why do we do all this work and try to design the infrastructure for organics recycling? It's for environmental reasons, and it's for trying to mitigate fugitive emissions from landfills in the United States. It is it's the third largest emitter of methane in the U.S., behind oil and gas and enteric fermentation, so cow sourced methane, and other four-legged animals. And so the difference between those other two sources is that the majority of that food scrap comes from our kitchens. So it's actually an opportunity for families to participate in reducing their carbon footprint directly. You can't really participate in that for oil and gas leakages. You can't really do it for big farm operations. But in terms of what you eat in your own household and how you dispose of those food scraps, that's the opportunity for the average consumer to try to do something different.
So what is that different? How do we do it different?
Yeah, and that is the billion-dollar question, I think, because it's a very fragmented infrastructure for collecting organics recycling, I think, in any developed nation. But really in the United States, and even in the state of Georgia, we have the most counties out of any state. And there might be a different policy in each county, in each city sometimes. So you have to think about what system you have to work with, and it's a fragmented system. So we want to look at what system will work, what type of organics recycling system will work that scales from middle-sized cities up. We want to understand how small cities do the organics recycling, but really where the need is and the population is in the middle-sized cities and the large cities. And the collection gap is for single-family homes or single dwelling homes, really. So it might be duplexes as well. There are plenty of solutions for medium density and high density housing when it comes to organics recycling. There are machines that accelerate composting. The technology is available. It's whether or not there's a will to invest in it. So we're really looking at where the largest gap is, which is about 55% of Americans, and that's the single family homes or dwellings. And it's how most of us live in the United States, and that's where most of the collection is not available. So the city is our hauler. That's Athens Clarke County. They're our partner. And we looked at 400 homes, and the demand was greater than 400. I'm not exactly sure yet. The pilot just ended in May, so we're writing up a report. But the demand was larger than what we could service, which is about 18% of the houses.
Okay. And so what are some of the, I guess, do you have a line of sight in terms of how do you handle organics collection and regeneration or organics recycling in that demographic of a size city? Like, what are some of the ideas that we'll see coming along that could start to get some momentum behind it?
I mean, it starts at the city commission level, I believe. So it's really what we're going to garner from this study is as we're writing up our report is an understanding of the financing of this program, because ultimately that's what taxpayers want to understand and what their tax dollars are doing. And that's not fully understood and fully vetted yet, and from the results of our pilot.
What was the response from the consumers on the education, the interest, the participation? What's the general sense from this study that you can share?
Yeah, so I'll give a lot of credit to ACC and their team. That's our municipality, Athens Clarke County. They did a fantastic job of communicating to their customers, because at the end of the day, they're not UGA's guinea pigs. These are customers that already are paying for roll cart services, so they are the ones volunteering for this trial, and the city ran a survey, and we're getting some of the results back now from both a mid pilot and end of pilot survey that was very positive. We had a 95% positive communication outcome when it comes to the communications about the pilot, when it comes to service time, questions, missing cans, response times. So ACC had an A+ for communication, and I think that's probably the most important understanding that will garner success. Is you have to have really good communication with your pilot participants, and they'll have a positive outcome as well. That also helps on the back end when it comes to contamination and communicating contamination problems. And at the beginning of the pilot, understandably, and we expected some contamination, and there was. And the contamination that really continued to the end of the pilot was printed cardboard. So everything else was pretty good. They did, in terms of logo certified, TUV certified, or BPI certified packaging that is compostable. We had high compliance in that regard. So that was a plus. But when it comes to what type of cardboard wound up in the stream, we had a lot of printed cardboard, and that's really material that we want to divert to recycling, not to the compost stream. So that's our main contamination problem, which is actually pretty good.
And if it's printed, there's a good chance it's got polyethylene on it, which is going to delay its breakdown as well. So
exactly, and it ultimately winds up being a direct input of microplastics. And this is not something that's commonly understood by consumers. I'm sure if you put a printed cereal box in your backyard, it will disintegrate, and you won't be able to find it several years from now. But there will be countless number of microparticles of polyethylene and other non-degradable polymers that have been deposited in that spot, and that's what we don't want to happen in the compost stream.
So, at what age do consumers get it? And is there an age demographic that believes in this? Like I always joke that you take somebody 30 to 40 years old, they don't have to old white guy intellectualize why this is important and why you do it. So I feel like they're kind of born with it. So what did you have any takeaways from that side of it?
Yeah, great question. So we ACC did capture the demographics of the pilot, and it spanned a pretty large age range. Of course, because of our proximity to the university, there were some more students than normal, maybe a little bit biased in the student population, but this is working families and working professionals for the most part, 3.5 heads per household, so average size families. And really the great part is the minimum education level is about that of a 4-year-old. And we're able to capture those learnings from the participants. There was a lot of qualitative data, a lot of stories that basically came in describing the joy that it brought their children to learn how to compost, because they knew they were doing something better for the environment about at the age of 4 or older. So that was a positive for sure.
And knowing that you have a 4-year-old son, are you educating him at home?
Oh, absolutely. Yeah. He knows all about the different waste streams.
Nice.
He helps out. He helps out in the kitchen, which is great. And also, that's one of the other understandings that we didn't really target, but came out of the program, is that when you monitor your food scraps going into another bin, you tend to have a better meter of how much you cook and what you are cooking with. So one of the qualitative learnings from the study is that people were changing their diets for the better and cooking more at home and spending more time with their family, and all these other kind of like soft positive outcomes that came from the pilot. And I mean, sure, we reduced 17.7 metric tons of carbon from the pilot, which is what the calculation comes out to be so far in terms of carbon reduction. But really, the important part is that there's joy being brought to 4-year-olds.
That's awesome. That is a really, really exciting piece of information from the study. And it makes me think, I think the study just came out. We're getting, I guess, better science around exactly how big of a problem food waste in landfills is. So I think there's going to be even more energy to divert it from landfills. And then you divert it to what? You can divert it to composting. You can ferment it into, lactic acid, for example, to make polylactic acid. There should be a myriad of ways that we take those intact polymers that nature has made and valorize them in new ways. And it all happens there, where it's been going to create methane in a dump. Now we can valorize it into other things. So somehow I think that's the genesis of how we rethink it, right?
Yeah, and it's you kind of pointed on methane generation from the landfill, and that's kind of what it all goes back to. And there are technologies that have methane capture in the United States, and burning that energy to, burning that fuel to create energy for homes. It's even done here in Athens. But that's less than 1/5 of all landfills in the United States. There's about 500 landfills that do it in the US, give or take some, and there's about 2,600 landfills in total that are registered by the EPA. So it's a minority operation. It's not the status quo.
So I'm not going to
that's not
age
always
my
a solution.
I don't want to age myself, but I will say that the landfill that I grew up around and the landfill closest to me here in Cincinnati, Ohio, I have watched over decades them getting rather noticeable from any direction. They're getting big.
Oh yeah, they're sometimes the largest and tallest feature around. They kind of stand out of the landscape.
Yeah.
But yeah, there's a lot of costs to opening up new landfills, and if we're going to consider, keep being consumers and produce a lot of waste, we have to consider that investment from 30 years from now.
Well, I have hope, and I know you do as well. And it's just really exciting to have you on today, Evan, because you and I met. We probably had a beer stressing over this challenge of understanding the micro consortia in the piles and what they like, what they don't like, and it led to writing up an idea. And you had that idea written up when Walmart Foundation come knocking on the door, 2 days before Christmas, saying, "You got anything we can invest in?" And what attracted them was it was a university, a materials institute, and a private sector company saying we should try and to see that progress to the point that we're actually trying to solve these system problems in the small, medium size, which you said 55% of Americans are represented in that demographic. I think it's a really important statistic. Just to see something that went from an idea to some thought behind it to where it is today is just I give you all the credit in the world, Evan, because you're the one that's been behind it. So I applaud you for that. I think the University of Georgia is doing wonderful things. I think the new Materials Institute is something that we desperately need. And I'm not sure as many that should know about it knows about it. So maybe this would be a way that we can get new Materials Institute a little bit more awareness in the market.
Yeah, well,
So again,
thank you very much, Kelly. That's very kind words. But I want to also thank everyone that's involved in the private sector as well, because there are champions in this space, and I think you're one of them in terms of communicating the need for private public partnerships, and understanding the value of that arrangement is very rewarding, I think.
So keep up the good work, Evan.
Yeah, thanks, Kelly.